Welcome protein coders, let's build some coding muscles. Today we're gonna see topological sort using BFS, famously known as Kahn's algorithm. So as we studied earlier in topological sort, the node which came first will be written first, right? So let's write the topo sort for this graph, which will be nothing but 0, then 1 came, after 1, 2 and 3 came, and we can write interchangeably. 3 also we can write first before 2, then at last 4. Okay, if you look carefully, we can also interpret this graph as like 1 is dependent on 0, 2 and 3 are dependent on 1, and 4 is dependent on 2 and 3. So we will use this concept and see how we're gonna do it using BFS. First, let's calculate in degree, means the incoming edges on a node. So for 0, the in degree will be 0 because there is no incoming edge. Then for 1 is 1, for 2 and 3 it's 1, and for 4 it's 2. Okay, now we will write independent nodes first. You can see this analogy, like the independent ones will be the parent and the children will be the dependent ones. So we will write independent nodes first, then the dependent ones. You can see that 0 has in degree 0. That means it's independent. It is not dependent on any other node. So we can write this in our topo sort. We can process this. After processing 0, we will move to its neighbor 1. At 1, you can see 1 is dependent on 0, but 0 we have already processed. So this implies we can reduce its in degree by 1. What that implies is now 1 is not dependent on 0 because 0 we already processed. Now 1 is an independent entity because its in degree became 0. So now we will process 1. And similarly, if we go to 2 and 3, their only dependency, which was 1, already processed. So now we can reduce their in degrees by 1, then their in degrees will become 0, which again means they are now became independent. So we will process them as well. And we can interchangeably write 3 and 2, right? Now from 2, when we move to 4, we will reduce it in degree by 1 again, because we have reduced one of its dependencies, which is 2. Okay, then when we move from 3 to 4, we will again reduce its degree by 1, which means we have removed one of its other dependency, which is 3. Now it became 0, so it became independent. Then we will process 4 also, and voila, this is nothing but our topo sort, right? Let's see once again how we did it. First, we are at 0, right? And we process 0 because it is independent, it has in degree 0. Then we move to 1. 1 has an in degree of 1 and it has a dependency on node 0, but because we process 0, the dependency on 1 has gone and we reduce its in degree by 1. So this will become 0 and it will become independent. So we will process 1 as well. Then from 1, we travel to 2 and 3. And because the 1 dependency is removed, the in degree of 2 and 3 will become 0. Then we will process them because they became independent. And finally 4 became independent because both of its dependency, which are 2 and 3, got processed. So if you observe, we are doing nothing but a BFS traversal here. And what we are doing during BFS is removing the parent dependencies in every next level, that is reducing the children nodes in degree by 1. Okay, I mean reducing their in degrees. And then what next thing we are doing is whoever or whichever nodes in degree became 0, we are gonna process them in the next interval. Okay, because they became independent. And in topo sort, the node which became independent first will be written first. Okay, just remember this thing. And based on these two things, these two observations, we want to write our topological sort. So let's have a note here that the nodes who will become independent during our BFS traversal will be processed first. That's all. That's our topo sort. Now let's see what will happen if we have a cycle. So let's write in degrees first. 0, 2, 1, 1 and 1. So let's start our BFS from 0. 0 has in degree 0, so we will process 0 and then we will move to its neighboring node, which is 1, and because we process 0, so we will reduce the 1 in degree by 1 because we have reduced one of its dependency, so its in degree will become 1. But here see carefully, it doesn't become 0. So what does this imply? It is not still independent, so we can't process further, we have to break from the loop. So our topo sort will have only one element. So from here we got a very important observation that whenever there will be a cycle in the directed graph, we have the number of elements in the topo sort less than the total number of nodes present in the graph. In short, we can say that topo sort dot size will always be less than number of nodes. Okay, and this is what is cycle detection in directed graph, right? If you observe carefully, we have detected a cycle in a directed graph using BFS, and this is one of our problem which we left earlier, right? So here you can see that we will perform the topo sort, and whenever there will be a cycle present in the directed graph, the size of the topo sort will always be less than the number of nodes. And we can't have a topological sort in order in our graph. So it's a byproduct of the topo sort, Kahn's algorithm. So that simple it is. Now let's see how to implement these observations in our code. Okay. So the step 1 will be, we will define our in degree vector in which we want to store the in degrees of all the nodes. Then a topo vector in which we will store our topo sort. So step 1, let's fill our in degree vector. So in your adjacency list, for every edge, okay, for every incoming edge, we will increase our in degree. Now second step, remember one thing, we can have multiple independent starting nodes in a graph, in a complex graph. So before starting our BFS, we have to push all of those independent nodes in our queue. So whenever we find the in degree 0, we'll push it into the queue. It's similar to multi-source BFS, which we studied earlier. Now let's move to step 3. Let's start our BFS traversal while loop, while queue is not empty. First we will get the node, okay, and node q dot front. Then we will pop it out. Then we will process this node, okay, we will push this node into our topo sort vector. Now let's travel for the neighbors, and what we will do is for every neighbor we are visiting, we will decrease it in degree by 1 because we are reducing its dependency by 1 for this node. And whenever we find a node, neighboring node with in degree 0, we will push it into the queue for processing further. Okay, and that's it, our topo sort is finished. But one important observation, we can only return topo sort only in one condition, when the topo sort size will be equals to the number of nodes. And here only, if you are writing code for cycle detection in directed graph using BFS, you can directly simply return topo.size not equals to n. That means we found a cycle. So this is for cycle detection. Now let's revise what we have studied today. So in Kahn's algorithm, what we are doing is we are performing our BFS, and whenever our nodes are becoming independent, or in other terms, their in degree is becoming 0, we are processing them or adding them to our topo sort. Then we saw if we have a cycle in our directed graph, the topo sort size will always be less than the total number of nodes. And this is how we got the method to detect the cycle in directed graph using BFS. Then we saw the code for this. We will have our in degree vector, okay, and at first we will process our in degree, okay, we will count the in degrees in our graph. Then we will push all those nodes which are having in degree 0, which means they are already independent. We will push them into our queue, okay. Then we do our traversal, okay. We will first get the node, pop it out, process it, and then we will check for its neighbors. Because we already processed their parent, so we will reduce their in degree by 1. And if their in degree became 0, which means they became independent, then we will push them into our queue for the further processing in the next cycle of the loop. And at the end, we will return topo sort only when its size is equals to the total number of nodes. Otherwise, we can't return it. Otherwise, there is a cycle. And we will use this observation to detect cycle in directed graph using BFS. So that's all from my side, guys. If you have any further questions or any doubts, please comment them down. The solution and the problem link you will find in the description box. If you don't understand, don't like, don't subscribe. But if you do, please show some support. Keep smiling, keep practicing. Thank you.